Hello, a very good morning, students. Today we'll start with a new chapter, that is 12th chapter of 12th standard, that is Electromagnetic Induction. So now let us have the review what we have studied. So what is the force on a charge when it is placed in the magnetic field? We have seen that. Also, what is the torque experienced by a coil or a current carrying coil when it is placed in a magnetic field? That also we have seen. Then we have also seen what is the magnetic dipole moment of the magnetic field or in the of a current loop. So we have seen this last lectures. So last two chapters we have seen magnetic fields due to electric current. That is, we have seen that when by using the Boyer's experiment, as we know that when the current is passed in the coil, we get magnetic field or magnetic field is developed because of the loop in a loop in a closed circuit, loop or a closed circuit, you can say. And secondly, or even you can say because of the electrons which are moving in the atom, we get the magnetic field that we have seen. Now, Oersted and Ampere, they performed experiments and found that because of electric current, there is magnetic field developed. But they afterwards they found there was the relationship, like they were interrelated, electricity and magnetism. And also we know that for generation of electric field, we require the charges which are at rest. But if the charges are moving, we have the magnetic field. Then later on in 1831, Faraday and Henry, they performed some experiments and found that because of the changing magnetic field, the current is electric current is developed. So this is the converse effect. So here we can see that they performed a lot of experiments and found that because of the changing or changing magnetic flux, you can say rather, the electric field was developed, or we can say we can see the current in the loop because of the changing magnetic field. So now, because of this, they came into conclusion that EMF is developed and there is induced current, and the main law which Faraday he showed, that is the Faraday's law. He proved this Faraday's law, which is a very important law. In this, there are two laws. So first, before seeing that, we'll go for the slides. The chapter which we are going to take is Electromagnetic Induction. This is the 12th chapter. Then we'll have a recap. We have seen that what is the force experienced by a moving charge in a magnetic field. So we know what is the force. F is equal to B E V. And then we have what is the torque experienced by the current loop. So see, this is the you can see this is the coil here, and there are two magnetic fields here. This is the north pole, this is south pole. So when it is placed here in that, we can see that it experiences a torque. We have seen the relation, so that is mb sin theta. tau is equal to md sine theta. And also, what is the magnetic dipole moment? So for a moment, dipole moment of a current carrying coil, so you can see this coil is moving, and this I is equal to mu a. No, sorry, mu is equal to magnetic dipole moment. Mu is equal to IA. So this is the relation, which is a very important relation. So I have told you that Oersted Ampere and others found that electricity and magnetism are interrelated. See here, electricity and magnetism are interrelated. It's very important. And we have seen that Oersted's experiment, in which when when a coil is carrying current, and if a needle is placed near it, this experiment is quite easy one, that. And then when the current is passing through the coil, it gets deflected. The needle gets deflected in one direction. And if the current direction is reversed, then the needle, it moves in the opposite direction. So this experiment is known to us. So because of electric field, there is magnetic field. So they thought, Oersted Ampere, is there any converse? Converse in the sense, is there electric current due to magnetic field? So that we are going to see in this chapter. And Faraday in 1931, Faraday and Henry demonstrated that electric currents produced in closed circuits or coils were subjected to time-varying magnetic field. So electric current was produced when magnetic field was changed, then we got the currents. Then the experimental observation of Faraday we are going to see now, and he also proposed a Faraday's law, that we'll see it later on. Now, magnet and coil experiment. So this is very simple experiment, so you'll understand exactly what it is. So see here, the magnet is there, bar magnet. You have played with this. So the magnet, bar magnet, and this is the coil. So this coil is in such a way that there is a galvanometer. So because of the change in current, it shows deflection. So when a magnet approaches a coil, so see here, if the magnet is approaching a coil, it produces a current in it. It produces a current, and this current is known as induced current. And then when the current is flowing in this, the galvanometer, it shows the deflection. Galvanometer, it shows deflection. And if the magnet is taken back, now this was taken towards the time the current is shown like this, but if the magnet is taken little back, again there is because of the changing magnetic field, the current is again induced, but it is in the opposite direction, remember. See, when the magnet is taken away, a current is again produced, but in the opposite direction. Now, in that experiment, now we saw two cases when magnet is taken closer and once the magnet is taken away. But the same thing happens if you take a coil and it is moved now. The magnet is kept at the fixed distance and the coil is moving once it is taken towards. So when it is taken towards the magnet, it will show the induced current in some particular, the induced current is shown in the direction, and it is shown the moment, galvanometer shows momentary deflection. And again, when the coil is taken away from the magnet, again the current is induced but in opposite direction, and the galvanometer shows the deflection in opposite direction. Remember this. Then, if the polarity of approaching or receding magnet is changed, the direction of induced current in the coil is also changed. So remember this, children. Now, first we saw about the magnet, it is moved closer and taken away. Then secondly, we are taking the coil, taking closer and moving it back again. And then thirdly, we are taking the magnet, the same magnet, but only the polarity. First, the south pole was near the coil. Now we'll have north pole near the coil. And if we just bring it closer to the near the coil, what happens? See, the polarity of approaching or receding magnet is changed. The direction of induced current in the coil is also changed. So remember this. So, and the main thing, these are the three things which we have seen. And fourth one, the important one is the magnitude. The magnitude of induced current depends on the relative speed of the coil with respect to magnet. It also depends upon the number of turns in the coil. So first it depends upon the speed, and secondly it depends upon the number of turns of the coil. So that is very important. So you can see the number of turns here. Then the induced current exists so long as there is relative motion between the coil and magnet. So induced current is present. Induced current means which is forcibly put, you can say, induced. So this current is present only when there is a relative motion between the magnet and the coil. This is the coil and this is the magnet. This is the experimental setup. This is the experimental setup shown here. Then we'll have the other two coil experiment, that is in which instead of magnet now coil is taken, other coil is taken. So it is coil and coil experiment. Now here you can see this, there are two coils. This is a coil for which we have attached here a rheostat is there, then there is a battery and a key. So battery is attached to this coil, so it is called the primary coil. It is called a primary coil. The other coil here, which has galvanometer at the other end, is called the secondary coil. So one primary coil is connected in series with a battery, rheostat and key, while the ends of the other coil is connected to a galvanometer. So remember, this is the secondary, this is the primary coil. Coil 1 is the primary coil and coil 2 is the secondary coil. So remember, now this is as good as the magnet. Now we'll see the three changes. First, when the circuit is closed or broken. Remember, when the circuit is closed or broken, by the key we can do this. When the circuit is closed or broken, the direction of the deflection in the galvanometer are opposite to each other. So the deflection which we see, once the key is closed, it will deflect in one direction, and when the key is open, again there will be a current, it will be in opposite direction, so it will show the momentary deflection in opposite direction. So remember this. Secondly, when there is a relative motion, now see here, this coil, this like magnet and coil experiment. Now if there is a relative motion between the two coils with their circuits closed, okay, these two coils, and induced current is produced in the secondary coil, and induced current, because of the first coil, there is induced current in the second coil. Remember, when they are in, there is a relative motion, you can see, between the two. Whenever the current in the primary coil is changed, now we can change this, either it is increased or decreased. How you can do this? You can do this by rheostat. This is a variable resistor actually. So by changing the value of this, that rheostat, if you just move or just slide the rheostat jockey, then a deflection is produced in the galvanometer. So in this case, again, so you have understood the three cases because of which there is the deflection in the galvanometer. So when is the deflection in the galvanometer seen? When there is an induced current because of the coil, primary coil. There is induced EMF. You can see even EMF is developed because of this induced current. Now when this rheostat, first we'll see about the key. So when the circuit is open or closed, there is momentary. We'll just repeat again. When the circuit is closed or broken, the direction of the deflection in the galvanometer are opposite to each other. Okay, if it is once right, then next time if it is closed, it will be the right side. So like this deflection. And when there is a relative motion, secondly, when there is a relative motion between the two coils, with the circuit closed, and induced current is produced in the secondary coil. And thirdly, when the current in the primary coil is changed, how can we change that? We have to change the value of resistance. So because of that, current is changing. It is either increased or decreased. By Ohm's law, we know V is equal to IR. So if you are changing R, automatically I is changing, increasing or decreasing. So by sliding the rheostat jockey, a deflection is produced in the galvanometer. So in this way, the three cases we see that the galvanometer shows deflection because of the induced current in it. So this is one of the experiment. Then here it is shown diagrammatically. The two coils are brought near each other when it is open and when it is closed. So these magnetic lines of forces are there. So you can see the animation of this. Here there are two coils, and here you can see that these are the magnetic lines, or you can say the magnetic flux rather. The flux is nothing but magnetic lines per unit area, or magnetic field per unit area. Now, third, that is Faraday's law of magnetic induction. The second point which we are going to discuss. First is the introduction and the experiment. One is the magnet and coil experiment, and second is coil experiment. And then we have Faraday's law of electromagnetic induction. Now, what is this law? This law, it is whenever there is a change of magnetic flux in a closed circuit, and induced EMF is produced in the circuit. So this gives the qualitative value of the characteristic. Okay. So whenever there is a change in magnetic flux in a closed circuit, and induced EMF is produced in the circuit. And second law is the magnitude. The magnitude of induced EMF produced in the circuit is directly proportional to the rate of change of flux, magnetic flux linked with the circuit. So remember this. So the second law is about the magnitude. The magnitude of the induced EMF produced in the circuit is directly proportional to the rate of change of magnetic flux linked with the circuit. Now see here, we'll just derive in short. If phi is the magnetic flux, remember, phi is the magnetic flux linked with the coil at instant t, then the induced EMF E is proportional to d phi by dt. Induced EMF is proportional to the rate of change of flux, isn't it? E is proportional and induced EMF is produced, isn't it? Because of the current, induced EMF is produced, and that is E is proportional to d phi upon dt. D phi means magnetic flux, number of magnetic lines. And the second law, then we have, if this is proportional, so second step comes with the proportionality. So E is equal to K times d phi by dt, where K is the constant of proportionality. If K is equal to 1, and if E, phi and T are measured in the same units, same system of units, that is SI units, you can say E is equal to d phi upon dt. So if we combine these two equations, we have, if phi dash is the flux associated with the single turn, see now, we'll take phi dash, this is the flux associated with the single turn, then the total magnetic flux phi for the coil consisting of n turns is phi is equal to n phi dash. So remember this, if phi dash is the flux associated with a single turn, then the total magnetic flux phi for the coil consisting of n turns is phi is equal to n phi dash. And then we'll write this equation, E is equal to, we know, E is equal to minus n d phi dash by dt. This is the flux law. And in SI units, E is measured in volts. You know, the SI units is measured in volts. This E, it is measured in volts. So this is d phi by dt. So phi is the flux. So flux is nothing but Webers per second. So this is very important law. That is the Faraday's law. After this, we are going to see the Lenz law, which gives the direction of this law, whatever is the Faraday's law. So we have seen that Faraday's two laws. Once again, you'll see that. So whenever there is a change of magnetic flux in a closed circuit, and induced EMF is produced in the circuit. So this we have seen. And second, the magnitude of this induced EMF in this circuit is directly proportional to the rate of change of magnetic flux linked with the circuit. So E is equal to, we have seen that E is proportional to d phi by dt, and that is E is equal to constant K d phi upon dt. So this is very important, the Faraday's law, and we are going to see this. After this, we are going to see the AC circuits also, which has by this principle applies for all that. And second is the Lenz law, which we are going to study. So in this way, the Faraday's law is a very important in this electromagnetic induction, Faraday's law. And for assignment, so you may write down that what is Faraday's law, what are the two laws, these two laws, please write down. And sometimes it's asked what is the Faraday's law, and give its SI unit. So what is this SI unit? You know, E is equal to d phi upon dt. So E is in volts, but d phi by dt is what is Weber per second. So this is a very important concept which you have to understand. Once you understand this, it's very easy to understand the other concepts also. So I hope you have understood this, children. Go home, take out your textbooks and go through it, study thoroughly, because everything we cannot cover in these lectures. Most of the things are that you have to do is the self-study, which is very important for you students. Hope students you have understood this chapter, electromagnetic induction, in which we have seen that in the before these two lectures we have seen what? Once again I repeat that how because of the electric field this magnetic field created, and now in this chapter we are going to see how because of the changing the varying magnetic field or varying magnetic flux, we have EMF induced in the circuit, and this is given by Faraday's law. And next lecture we will see what is Lenz law. So please go home, please sit and read this thoroughly so that you will understand. This is enough for today. Thank you. May God bless you.